Today's lecture on function of random vector. So this is very important and useful thing in statistical theory and as well as in application. So function of random vectors. Now we have some simple function like say x and y are two random variables. That x and y are two random variables. B two random variables. Two random variables. May not be random vector. Okay, first consider, let's consider the random variable, two random variables. That means x, y together is a random vector, two-dimensional random vector. Now, so defined on both the random variable defined on say same probability space, omega, script s, and the probability p. Now we define some functions like that important function, something like x plus. So x plus is a new random variable which it takes on input omega, it gives x omega plus y omega. Very simple, just addition of two functions, and that should be true for all omega, for all omega in omega. Similarly, x into y or x minus y omega is similarly x omega into y omega for all omega belongs to omega. Now, what about the division x by y? Two random variable x by y, division of two random variables. At omega it is just x omega divided by y omega, but this should not be defined if y omega is 0. So this is for all omega belongs to this. That provided it's given that provided that probability of or not the probability that y omega cannot be 0, provided that y omega equal to 0, thus omega does not exist. That is a phi set. For every omega, y omega not equal to 0. Now, what is the important theorem? Theorem is this. The proof is in any standard book. In Rohadga also is there. I do not give the proof here. The theorem is this: if x and y are two random variable, then this x plus y, x into y are random variable, are random variable, random variables. Further, if that set y equal to 0, that y equal to 0, this set also we can write y equal to 0. Same thing, by notation we can write this y equal to 0. This is phi. Then x by y is also a random variable. Is random variable. So this is very important. The proof is the addition proof is easy, but the product and these others are slightly complicated. Should not go with this proof. You can easily check, see in the book. Now, next theorem is important. That say we consider say this sequence of random variable, or maybe the n random variable. Let x1, x2, xn be random variables on this omega, script s and p. Define mn equal to maximum of x1, x2, xn. And what is the definition of this? Mn omega is just maximum of this this x1 omega, x2 omega. You have this maximum value of this. For all omega in omega in sample space. Similarly, define yn as a minimum of yn as minimum of these random variables, minimum of x1, x2, xn. And similarly, now note that this is easy to see that it yn nn is nothing but if you take the negative of this all this x1 x2 xn minus of that. Now then if you take the maximum of this, the minimum of x1 x2 xn, it will give the maximum then. So say like say 2 3 5, then if you take minus 2 minus 3 minus 5, then minus 2 is the maximum. 2 3 5 2 is the minimum, but minus 2 minus 3 minus 5 2 minus 2 is the maximum. So if it's the maximum and then again take the minus, then you will get the minimum. So the minus of the maximum of the minus. So that means if maximum is a random variable, then minimum also random variable, because x1 x2 xn random variable, then minus 1 minus x1 minus x2 minus xn is random variable. Now if we can prove that the maximum is a random variable, then the maximum of this x1 minus x1 minus x2 minus x is random variable, then minus of that is also a random variable, that is the minimum is a random variable. So we have to just show it is maximum is a random variable. Again you can see in the book. Now this is very important, that this result, this theorem is mostly, I think it is a very important for joint density or to find some other higher dimensional densities or distributions. So if x1 x2 xn are independent, let this be independent random variables, then for all z belongs to real number, the probability of the maximum value of this x1 x2 xn less than or equal to z. What is this? The maximum is less than or equal to z means the everything is less than or equal to z. The everything, the probability of x1 less than or equal to z, x2 less than or equal to z, xn less than or equal to z. Every value is less than or equal to z. But these are independent, that means the product. So the product of I equal to 1 to n, the probability of xi less than or equal to z. This is very important. Now what about the minimum? The minimum is this. So that probability of the minimum mnn greater than or equal to z. The minimum is greater than or equal to z means every other value is greater than or equal to z. Every value, every random variable is greater than or equal to z. Now what is this? If this is independent, there is a product of I equal to 1 to n, probability of xi greater than or equal to z. Now what is this? This is but what is this probability of this? This is 1 minus probability of n. We can also take just strictly greater than, strictly greater than, strictly greater. Now this is just 1 minus nn less than or equal to z, the complement. What is this? Now again it is just product. So it is product of I equal to 1 to n, the 1 minus probability of xi less than or equal to z. And this is the 1 minus probability of nn less than or equal to z. Now what is this? That means probability of nn less than or equal to z, the distribution function of the minimum is just 1 minus the product of I equal to 1 to n, 1 minus probability of xi less than or equal to z. So this is very important, and the corollary is a very important corollary is this: if these are independent, is a common distribution. That means IID. If x1, x2, IID independent and identical distributed with common density function or common distribution function with common distribution function. Say f, the distribution function f, that means the probability of xi less than or equal to z is x. Then the probability that the distribution function of mn, the maximum value is just f to the power n. So everything is the probability of xi less than or equal to z. This is actually fz. So it is f fn to the power z. That means it is actually fz whole to the power n for all z. And what of the minimum? The probability of the minimum value is less than or equal to z is just 1 minus fz whole to the power n for all. So this is very, very important. And now if there is a density function, if this is a continuous, so if they are continuous random variable, if f is absolutely continuous, if these random variables are continuous, then the distribution function is absolutely continuous. And the density function is PDF is small f. Then what happens? Then just this probability of xn, mn less than or equal to z. This is just f of z whole to the power n. Now this is the probability, that means the distribution function. How do we get the PDF? Then the PDF of mn is, say it is say gz. We know this is the derivative of the distribution function. This is the derivative. We know the derivative of the distribution function is the density function. Now if you take the derivative, it is just n into f to the power fz whole to the power n minus 1, and the derivative of fz is just small fz. Small fz is a density function of that x1 x2 xn, the common density. Now similarly, the probability of nn less than or equal to z is 1 minus that 1 minus fz whole to the power n. Now if you take the derivative, then you will get the density function. So PDF of n is, say h function is what is the derivative? Now how to take the derivative? So derivative 1 derivative of the 1 is 0, so this is minus n into 1 minus fz whole to the power n minus 1, and then the derivative of 1 minus fz, which is just minus of fz, so minus is cancelled out, it will be plus. So it is just this n into 1 minus fz whole to the n minus 1. So this is a density function of that minimum value, and that is a density function of the maximum value. So this is a very, very important thing. So this is some function of maximum minimum function of some n random variables. Now say consider one example. Now consider one example of continuous thing. So what will be the common density? What will be the common density of minimum and maximum? What is the common density? Now the common density will be, so if the result is this, that x1 x2 xn are IID with common distribution function f with common distribution function f and density function PDF of is small f, then the probability of mn less than or equal to x and nn less than or equal to y, the joint density, joint distribution of a minimum and maximum. What is this? So the minimum value is less than or equal to x, and the maximum value is, maximum value is less than or equal to x, and the minimum value is less than or equal to y. So what is the value? The value is this: if it is x greater than y, then what happens? So if x greater than y, so some value say x is 10 and y is 3, so the maximum value is less than or equal to 10 and minimum value is less than or equal to 3. That means at least one value is less than or equal to 3 and all the values are less than or equal to 10. So all the values are less than or equal to x and at least one value is less than or equal to y. And which is, what is this? This is just fn fx to the power n. Better we write in this fx to the power n minus that fx minus fy, the gap. Fx minus fy means the probability between x and y, between x and y. Now, if all the random variable in the probability in the x and y, then minimum cannot be less than y. So it is a complement. So it is just the minus this. And if x less than or equal to y, whatever. Now, so 3. The minimum value is less than or equal to 3. Sorry, the maximum value is less than or equal to 3, and so y is 10, x is 3, and y is 10. So maximum value is less than or equal to 3, but minimum value is less than or equal to 10. It is obvious. If maximum value is less than or equal to 3, then minimum must be less than or equal to y. So it is just the maximum less than or equal to x. And we know what is the maximum less than or equal to x. It is just what? It is just fn to the power fx to the power. No y actually. It's just if maximum value is minimum value is maximum value is less than or equal to x, then minimum value must be less than or equal to x, and therefore must be less than or equal to y. Now, if f is absolutely continuous, with PDF f, now what is the density function? Then we know the density function, the PDF joint PDF, then joint PDF of the maximum and minimum. We know how to find the joint PDF of two variable. We have to take the partial derivative. For single variable, we have to take the derivative of the distribution function is the PDF, and joint PDF is the partial derivative of the distribution function. So it is just say uxy is just the partial derivative with respect to del x del y of that fxy. Now what is this? Now if a two thing, if it's x less than or equal to y, then it is just 0. So if we take the partial derivative with respect to y, it is 0. It is 0 because there is no y. It's only x. If you take the derivative with respect to y, it is 0. Now, what about for x greater than y? X greater than y, in that case, you can easily check that is n into n minus 1 is a homework. Fx minus fy whole to the power n minus 2, and then fx into fy. This is very interesting result for x less than or equal to greater than y. You can easily check that. Take the partial derivative of this function, that fx to the power n minus fx minus fy to the power n. So take the derivative with respect to x first, then y. So it is actually when the derivative with respect to x is n into fx minus n into fx to the power n minus 1, then small fx minus that n into that fx minus fy, and then fx minus fy at the derivative with small fx minus small fx. If you have to take sorry, it is just fx, so because you are taking derivative with respect to x, so it is just fx, and again you are taking derivative with respect to y, then it will get n into n minus 1, and then the power will be n minus 2. Again, one more derivative, and in that case, that n into fx to the power n minus 1, it will go 0 when you take the derivative with respect to partial derivative to y. So that part is just vanish, and we will get this. So this is easy to check. Now, the interesting case is that maximum value and minimum value is not independent, right? Because the joint density function is not the product of the density function. Not the product of the density function. So they are not what is the density function? The density function is this. What the density function is given here. The density function of mn is just n into this, n into this. So if you take the product, then it is n squared into whatever fx, fz, fx to n to the power n minus 1, 1 minus fy to the power n minus 1, But this here it is not something like that. N into n minus 1. So these are different. It is not the product of the density function. So it is not the independent. It's obvious. Obvious. The maximum minimum cannot be independent. If maximum value is minimum value is large, then maximum value cannot be small. So they should not be independent. It is clear. Now we'll see one example, and it will be clear. Then much more clear. So one example is like that. Say let x1, x2, xn are random variables. Be random variables with say common density with common PDF. Probability density function is that is a uniform, say uniform from x to a to b. So it is b minus a when x belongs to a to b. A is less than b, and it is 0 otherwise. Now we can check that the density function of PDF of then you can check PDF of Mn is just this Gz is the two values. If Z is A to B, we have something, and otherwise it is 0. Again, same thing. Maximum cannot be otherwise. Maximum minimum obviously in between A and B, and you can easily take that derivative, and you can see from the previous result that it is n into Z minus A by B minus A whole to the power n minus 1 into 1 by B minus A. These are homework. You can easily check that, and the dense PDF of NN is that HZ. Again, this is 0 for other case, otherwise, and for Z equal to in Z belongs to A to B, what is the value? You can easily again check that it will be n into B minus Z by B minus A whole to the power n minus 1, and then that's the density function 1 by B minus A, that f Z, the density function. And you can easily check one more thing, that the joint density function of that maximum minimum value, the joint density function of the joint PDF of that Mn and Nn. This is again two values. If x less than y, it will be 0. Maximum value cannot be less than the minimum value, so it is less than 0. And when x is greater than y, but that what lies between this, actually we must say it is otherwise. We should say it otherwise, because it just better I say it is otherwise. Otherwise it is 0, and in that case x a is lies x and y is less than x and lies between this. Then it is just n into n minus 1 divided by b minus a whole to the power n and x minus y whole to the power n minus. You can easily check that. So this is one example. We can have several examples on that. Now the next theorem is for the multidimensional case. Let that f from Rn to Rn, now the n-dimensional thing, be a Borel measurable function. Is not the Borel measurable. Borel measurable function. Now, if that random vector, say is x curl random vector x1, x2, xn dot xn, these are random variables, and n-dimensional random vector is an n-dimensional random vector. Is an n-dimensional random vectors n greater than or equal to 1. It may be one-dimensional, just a single random variable. Then that function fx that is also in Rn is you can take as also Rn to Rn. Then this is m-dimensional m dimensional random vectors. So it is n dimensional vectors, and this proof is again in the book. This is not tough. You can easily check that. Like say x1 x2 x3 is some random vector of 3 dimension, and you can take 2 dimensional vector like say x plus y plus z with x into y into z. So product and sum. Sometimes this transformation is very important. Sign transformation. X and y are two random vector. You can take sin x, cos x, x plus x square plus y square, and that tan inverse y by x. That is also a polar transformation. So this is also called transformation. R2 to R2 transformation. Different type of transformation. Function transformation. So there is some function from R2 to R2. Something the one popular transformation like that. R theta. Say it is function of R theta. If R theta is just R sine theta and R cos theta. R cos theta, R sine theta. There is a polar to Cartesian, and maybe there is some Cartesian to polar. F of xy is just root over x square y plus y square and tan inverse y with some y positive given. Some conditions is there. So these are the inverse transformation, and when this inverse transformation exists, and this these are we have to know the implicit function theorem, and we obviously we need the Jacobian of this transformation. The Jacobian of this transformation is very important. We have to know the what is the Jacobian of the transformation, and we have to find the Jacobian of the transformation. We have to multiply it by that Jacobian. Then we have to find the PDF and density function, and this for the multi-dimensional case, the Jacobian that is the implicit function theorem is very important, and this inverse integral is also important from the real analysis. So these are important for the this transformation thing. Also for the discrete case, we can do this. And for this multidimensional continuous case, we need that Jacobian thing. So what will the Jacobian thing? Jacobian part. The Jacobian part is okay. We just stop here in this this lecture, and the next lecture we will go through the n-dimensional random variable x1 x2 xn and go with this the Jacobian thing. Say x1 x2 xn is the random vectors, n-dimensional vectors, and we take say u1 u2 un. So u1 is some the function of x1 x2 xn. Again u2 is another function of x1 x2 xn. Then we have to find the Jacobian and this partial all the partial derivatives and the inversion theorems and many more. The continuity of this partial derivative and all other things we need for the continuous case. But for the discrete case, it will slightly again very complicated. For continuous case, we can easily do it some Jacobians and this multidimensional multivariate calculus function of several variable. But for the discrete, it will be the summation, the multiple summation, and this double sequence, double series. That is very complicated thing is involved here to find this all this distribution of this function of random variable function of random variable.